Okay, Brunel transistor fans, this is Dr. Barry Ron, and I want to take you through the choice of should you use pi or T-model. And we're going to look actually at that exam question, which we touched on earlier in class. You'll also find out that this is related to that discussion we had on the resistance reflection rule. Topic at hand, what's the input impedance? That's what we're trying to calculate. What if I'd use the pi model? Well, I'd be talking about this circuit here. And we're going to see that it's a little less convenient for calculating input impedance. Why is that? Well, when we calculate input impedance, we're asking what's the relationship between this voltage here and the current that goes into this whole circuit. So if we redraw this, and we think about a little test circuit IX and test voltage VX, we're going to have something like this. Here's R pi, here's R1. Now, unfortunately, IX looks kind of complicated. IX is the current that's going into this resistor, plus the current that's going in here, minus this dependent source. It's all rather complicated looking. What if instead we'd noticed from the beginning that the emitter is grounded? Sorry, that the base was grounded. That would have been a good clue to use the T-model. In the T-model, if we try to answer the same question, what's the input impedance, we actually immediately get something pretty simple looking, because this is actually the circuit we have. The base is grounded, so the two halves of the circuit are pretty well separated from each other. When I use the T-model, it's really easy to calculate Rin. It's just R1 in parallel with Re. So it turns out it would have been smart to choose the T-model in this case. We're not stuck. We can deal with this circuit here. What we notice is, as when we discussed the resistance reflection rule, the dependent source is something that we really need to deal with. If we're calm and we apply all the rules that we know, we can still come up with the same numerical answer as we got down here, even though we're using the pi model. Let's give that a shot. So, here I was, stuck with my choice of the pi model. But because I'm disciplined, I can still get the answer. So let's have a look at that. Here's what we are faced with. R1, R pi, and what is thankfully a dependent source. It's beta times IB. What's IB? The current going through this particular branch, the branch with R pi. At this point, we can actually write down what is IX, because IX is really key to calculating the input impedance. IX is just equal to the current through R1, the current through R pi, and the current through the dependent source. So that's just Vx divided by R1 plus Vx divided by R pi minus beta times the base current. Fortunately, I know some things that relate the base current in R pi. I can notice actually that there's a relationship between Vx and VBE. Here's VBE. Because I know Ohm's law here, I can make a few substitutions. When I do that, I find out what is this base current. So notice that VBE is just the same as Vx, except its sign is flipped. So since this base current is just equal to VBE divided by R pi, I've got a relationship between VBE and R pi, and I can also notice that I've got a Vx here. Look at this picture that I've drawn. I've labeled the current that goes through this resistor, but the truth is, when we talk about base current, it's always from base to emitter. So actually, although what I wrote here about Ix is true, this IB is a very particular current. It's the current that flows from base to emitter, just like we see here. We know in active mode, current is actually flowing like this. So how can I proceed? Well, I've got a pretty good situation here. I just need to replace that I base. Let's rewrite what we have here. So what is the base current? Actually, it's minus Vx divided by R pi. If we work this through, we've actually got something like this. And we're finally starting to get something that looks like we could solve it. So what have we got here? A lot of terms with Vx and some R pi's. In particular, I want you to notice what happens when we do this. Really, there's two pieces of the current. The part that depends on R1 and the part that depends on R pi. If we don't rush to solve this, but look at it a little bit carefully, we notice something interesting. We've actually got what looks like another resistor. It's different from R pi by a factor beta. Do we recognize it? It's actually our friend Re. So by going through all these steps, we've gotten to the calculation that we could have done if we had used the T model in the first place. So to finish this, what's Rn? It's Vx divided by Ix. If I'm patient and I write this down, I see the Vx is actually canceling. And what I'm left with is simply 1 over R1 plus this other resistance. So to finish this off, if I cancel out from that last line, I've got 1 over 1 over R1 plus beta plus 1 over R pi. What this is just the expression for two resistors in parallel. So that's actually the same as R1 in parallel with R pi over beta plus 1, which is the same as R1 in parallel with RE, just like we achieved by starting with the T model. So flipping back, got a plus there. When we had the T model, we happened to choose a configuration that took advantage of the fact that the base was grounded. Have a look for that the next time you're solving a circuit. And the truth is, sometimes the T model will be great for one thing. Other times the pi model will be great for something. But other times when there's something on both sides of the circuit, you're going to have to use some arguments like the one that I just used over here, where you very carefully take account of what's happening with this dependent source up here. When you do that, you're actually using the resistance reflection rule.